Welcome guests. We are very happy to have such a big turnout tonight. We also are very fortunate that the fathers and mothers of our new bylaws wrote in a thing that allowed us, when we have an annual general meeting, to allow proxy votes, because we've got 14 people in proxy.
16 present and 15 proxies.
We've got a quorum, basically. So this tonight's talk is not all in vain. First of all, we're going to have a mini annual general meeting, and I promise it'll be under 5 minutes. So I need somebody to volunteer as a timer to see if I've done that.
NRC official sign.
And then we're going to have followed by 10 seconds of silence. So we're going to have announcements and talk about upcoming events, and then our guest speaker is going to talk about discoveries in the outer solar system. And we have a visitor from the outer solar system here tonight, and that would be comment C2018Y Iowa Moto. And this is a drawing of it by Bill Weir, and he did that on the 9th of February. It just happens that the closest approach occurs on February 13th, which is our today. So it's an interesting comet in that it's going to be 0.3 astronomical units away from the Earth. When it comes, its closest approach to the Sun, the perihelion, is 1. Astronomical units away. So the eccentricity is 0.099 almost. What does that mean? If you have a circle, your eccentricity is 0. If you have a straight line, your eccentricity is 1. So it's almost a straight line orbit here. So we're honored that it's coming around. And it has a period of 991 years. And so the next visit will occur on July 4th, 3010. And July
will still be president.
No, July 4th is important because that's Henrietta Leavitt's birthday.
Oh.
This all ties in with Women and Girl Astronomy Day. So we'll just build on that. And this is the diagram. I'm sorry I forgot my pointer. But there's a date there that says 2:13 and 2:14 is the position of the comet tonight, and there will be some clear breaks in the skies. And it's just the comet's moving about 5 degrees a day or so, or zipping along pretty fast. And it's just gone through the jaws of Leo the lion, and it's heading towards the heavenly twins, Gemini. So if you're out there later tonight, take a look. It's quite a faint comet, but Bill Weir has written up a nice report that he shared, and it looks like it's really worth a look. So this comet came from the outskirts of the solar system, and that's what our interesting talk with Sam Lawler is about tonight. But we first of all is our mini AGM, and I would like to call it to order at 7:38. And we have recorded members that are present. Have we had confirmation of a proxy?
We have a proxy.
We have a proxy?
We have quorum. We have
quorum.
Yes, that's right. We have 15 proxies, 60 members, possibly more. And so
we needed 25. We have more than that, and I would like anybody who is watching from home and voted by proxy, thank you so much for your important contribution. I really appreciate that. We did have proxies from all over the southern Vancouver Island, but one was farther than others. It came from Tasmania, and it was the first one we received today. So that just shows you the value and the miracle of the internet. So Ed, we're just gathering some interesting data and then we'll call the meeting officially to order at 7:39.
You keep changing the clock.
7:39. Time work.
Okay, the first thing is the approval of the minutes that were distributed on a previous email. And these are the minutes of our AGM that was held on November 17th, 2018. I've got 2019 there, so that's a bit of an error. And I would like someone to move that we approve these minutes. Chris, first. And a seconder. Lori Roche. And a discussion. No discussion. All in favor? Carried. Thank you. The next thing is the presentation of our quarterly report. I'm not going to read this, but I'll just highlight two things there. Why are we having this mini AGM? We changed our fiscal year end from September 30th to December 31st to make the Canadian Revenue Agency happy. We are having this mini AGM tonight to make the BC Societies Act happy. And this has caused a lot of work for some of the members of our council. We're probably not all that happy, but we're very happy to see you here tonight. So what we have is a quarterly report. Normally we have an annual report that we read out at the AGM, but the quarterly report is I've just highlighted our center meetings that we've had and our speakers that we had at them. And I mentioned Sid and Lori's contributions for the educational outreach activities, talked about observing sessions, and our membership during this period bounced around 275 people. But the one thing I do want to highlight, probably the biggest thing that occurred during this 3-month period of the quarterly report was on the construction of the heavens, a wonderful concert and a marriage of music and astrophotography that took place at the Christchurch Cathedral on the 16th of November, and it was a great success. And so that is our Victoria Centre report, and this was distributed to everybody, so if they want to read the fine print, they're welcome to go back. The next thing we have to do is the approval of the financial statement. And I really didn't know what an AGM really was all about. I thought it was about door prizes and plaques and banquets and stuff like that. The real business reason why you have an AGM is to approve the financial statement. So our outgoing president, Bruce, who was the guy who pioneered that we change our fiscal year end to the end of the year, caused himself a lot more work. So it was really a true act of altruism that he did this. And he has presented this statement of assets and liabilities, which is our financial statement for the 3-month period of this mini year that we're talking about. And Bruce can't be here tonight due to traffic problems on the Sandwich Peninsula, but it worked quite hard to get this together. It was shared and discussed at the January 16th council meeting, and it was approved then. So I would like, we've had a chance to examine this. I would like someone to move that we accept this financial statement. Dorothy? And Mike? Discussion? Yes?
I have a question from Sid Sidhu.
Yes.
If it's written, may I read this as part of the discussion?
Okay.
It is regarding the value figure of $7,060 for telescopes, donations, and public outreach. So the very first line in the statement of assets and liabilities. It seems too low considering the Ray brass telescope that's worth more than $40,000 that belongs at the center of the universe building. All other aspects of the statement seems to be all right. So I guess what he's asking is where in here is the value of the Ray telescope that belongs to the RASC?
Which telescope?
The big brass telescope that sits in the corner of the center of the universe?
Okay, I think we were looking at the operational assets of the BCO equipment when we were doing this thing.
No, it doesn't belong to the BCO, it belongs to the RASC. It's loaned to the center of the universe. It doesn't belong to the
I see.
Friends, or it belongs to the RASC. So I don't know whether anybody here knows anything of the history or of the value of that. But
it's never been factored in beforehand, but I think he's raised a good point. I would consider we give this a review because we have very expensive books that we've tried to sell for market value of around $7,000, and we have had zero interest. So potentially an item like this might have great value as a historic value thing, but it might be rather difficult to raise those funds.
No, I didn't sell. You wouldn't have any problem selling that
And for what price?
for $40,000.
You think so?
I've been to a Sotheby's auction.
Okay.
Yeah.
I guess it depends on how it's viewed. Now, in an operating context like this, you're actually looking at capital depreciation. So first of all, we didn't buy that telescope. It was donated to us long ago. And the normal depreciation period is up to 10 years for most things. So in fact, I would say in terms of this statement, it actually doesn't have a value. Now, maybe we need to account for it somewhere else.
Okay.
But,
And something that'll or increase in value.
yes, and that's very hard to determine. So we should insure it, I think, and we should report it somewhere, but it doesn't necessarily, I don't know if it fits in.
It was definitely not factored into our financial statements this year or any of the years that I have been president. Have you got any suggestions?
Well, the only weird thing about financial statements is that they start at what you paid for it and then they depreciate that. It's not actually a legitimate valuation. And so for insured value and book value are two different things. The financial statements generally cover book value, but in fact, you need to insure it for its real value. And there is a difference.
Okay, could that be somehow just reported in the minutes?
Can we just put that in the discussion of the minutes? That you raised the point that if a telescope is donated, it would have an initial value, book value of 0, even though.
And then it's depreciated. I mean, even if it was, we bought it, it would be depreciated at a rate that it may actually be appreciating, but we still depreciate it for, and then, but insured value is different.
Okay. Any further questions, Dorothy?
I believe it's right. I don't know if it's possible for this scope, but if we could get a value of it at the time it was donated.
Yes, we can do that. We don't necessarily have to value, but you still depreciate it every year.
That's right.
Yeah.
But there is a value.
There is a value. You're quite correct. As long as you get it certified by an external party, that's its initial value, and then you depreciate it. But its insured value could be quite a bit more.
Yeah. But there
Yes.
is a value for the time that it was given to us. In this case.
Okay. Having taken the argument for now, I think that we will revisit this topic at a later date. But at the point now, raised on Barbara's argument that it was a gift initially, and so its initial value of the gift was 0?
Well, unless we got an improved valuation done at that time.
Yeah, okay. So we'll leave it at that for now. So can we have a vote on the financial statements which reflects the primarily the assets of GRASC excluding that telescope, and see how many people are.
There'll be a note added to the financial statements indicating that that asset is excluded.
Yes, okay. All in favor? Opposed? Carried. Thank you. So I have an apology. Due to that time, we ran over by 7 minutes due to that issue. But I think we should blame Sid Sadhu.
Yes.
At any rate, now we're going to adjourn. Could I have somebody to adjourn the mini AGM? Jim Hesser? Okay, thank you. And we don't need a seconder for an adjournment. Adjournment was at 7:50. Okay. So thank you for all your patience through this minute of this thing. So the next thing is the announcement, and as a president, one thing that came to me was that we've moved the 20-inch beautiful Dobsonian telescope that was built by Guy Walton in 2003, and it is using a parabolic 20-inch mirror that came out of Jack Newton's telescope. And it is now standing tall in the center of the universe, so we could make room for a 20-inch obsession telescope that will be assembled and stored in the Victoria Centre Observatory. The other thing, let's see, Vice President, no report. Sky News editor, Bruce is not able to be here, but he's once again written a wonderful article in the Sky News for the February edition. So if you haven't looked at it, please give it a look. It's a great effort. And it has an interview with the rascal of the month who is here, and that is Diane. So she gave a lovely interview for that. Unfortunately, the treasurer, Deb, is not here. Her financial statement she emailed to me, but I can't access it right now. But we will, it was slightly over $14,000 in our main account, about $14,300, and our gaming account is at $20. So that's the financial statement. Membership, Chris?
So our current membership is 285.
285.
There are some people whose memberships have expired. We've got 2, 4, 6, 8, 10, 12, 14 people. So
In the grace period.
yeah. So minus 14.
But that's the highest it's been, I think.
Getting there.
Yeah, great. Thank you for that. Instead of having an outreach coordinator, we're trying something a little bit new, and we have an Astronomy Day team captain, David Lee. We held a meeting at Astro Cafe last Monday, and David is, we contacted all the major participants who normally come to this event, which will take place on Saturday, April 27th at the Royal BC Museum. And David is going to be following up with the people who signed up to support this event. And so we'll be moving forward on that shortly. Sid's not here for the school program, but Lori, do you have any statistics on how many classes you've
Well, the last 3 days have been school snow days. So I can tell you the number of times that we have not done programs in the last 3 days. It's full right through to the end of February, and then we'll be taking a break in March and then back again in May and June. So we're getting in there. It's getting filled up for sure.
It's an amazing program you guys do.
Yeah.
The tech committee, Matt.
The tech committee held a meeting on February 5th. And there was extensive discussion about the current state of the TPO 16-inch and its troubles with collimation. We have ordered another collimating aid. It's a Takahashi collimating telescope. Our hope is that as soon as this arrives, we can put it to use and resolve the issue. Anyone has any further questions about that? Talk to myself or Dan Posey. Aside from that, don't slip. It's cold up there.
We are going to have a work party to assemble the 20-inch succession telescope as well. It was planned for this afternoon, but we got a call from Clive Donnelly that saying that the road hasn't been plowed down there. So it might be a while before we're back at the VCO. We'll see what happens tomorrow with tomorrow's storm. So the website, Joe is not here, but it's humming along. Observing, Michelle is not here. And the National Council, Nelson is not here. So boom, there we go. That's the end of our announcements, except one thing, upcoming events. Astro Cafes every Monday night at 7:30. We had a notice about a space-themed art exhibit from Elise Longuer between February 15th and March 10th, and it's called Space Probe, and it might be interesting to take a look at. This occurs on Friday, February 15th. So the opening, that's between 7 and 10 p.m. at a place called the 50/50 Arts Collective on Douglas Street. Does anyone know where that is?
Yeah, it's near the suitcase repair place on Douglas Street.
That's great.
Okay. Okay, it might be fun to check that out.
Just a little bit beside Bay.
Okay. We had planned to have our International Astronomical Union Women's and Girls Astronomy Day session at Astro Cafe on the 11th, which was the actual day, but snow closed that down. So we're holding that on the 18th, and we've got a couple of things planned, 3 things. Randy is going to give a talk on Henrietta Leavitt and the Cepheid variable contribution she made. I'll be giving a talk on my hero, Vera Rubin. And we're going to have Barb and Kurt are going to be giving a talk on 5 major astronauts. Is that?
Might even be a couple more now.
Okay, well, an undisclosed number of astronauts they're going to talk about. So that'll be an interesting session. But if anyone else has got some story they want to talk about, females in astronomy issues and this sort of stuff, the Astro Cafe is a good place to raise that. So I hope you'll be able to make it. It'll be a good talk then. Now the Nanaimo Astronomy Association has an open house on Thursday, February 28th. They've invited a number of different agencies, including the Cowichan Starfinders group, our group, and they'll be having this open house from 6:30 until 9:30 on the evening of Thursday the 28th. I've been invited to give a talk. They'll have a table for us there to display stuff. So if anyone is interested, they're looking for somebody who's a passionate observer to share their enthusiasm with people. And so this is open to the public as well as other astronomers. So it's a great opportunity to make contacts with people all the way up the island. So it's kind of a mid-island rendezvous for astronomy, and it's the first one, and it'll be interesting how well it works. Our next next monthly meeting is on Wednesday, March 13th, and we're going to continue our Kuiper Belt theme because J.J. Cavaliers is going to be talking about Ultima Thule mission. He'll have the latest updates on that. And what else have we got here? We have a council meeting on March 20th, and Dorothy Paul will be giving a presentation at an event called Eco Literacy Day at one of the elementary schools. We discussed this at our last council meeting, and she made a very strong case that we shouldn't just look at the aesthetic benefits that light abatement affords astronomers. She made a strong case that the lack of darkness has a major impact on the health of all living things. So I think it's the kind of the combining forces with these people will even strengthen the argument for light abatement more. So she's giving a talk then. And finally, our astronomy day is on April 27th. So that's pretty much it. So, yes?
There's one thing that's missing from that, that's the science fair where we need, and Laurie and I and a couple others who are here, but we can always have more rascals to come and look across from 4th grade to 12th grade exhibits and decide which 3 or up to 3 we think are worthy of award from our center. And so it's a lot of fun. And anyone who's interested can ask me, look it up. Maybe when I get a notice, I can send it to you and you can send it around, because it's a lot of fun. I think we probably have a lot of new members who would be really good at that. And
yeah.
It's,
okay, thanks for sharing. Do you have a date for that?
it's the first Sunday of April, I believe.
So it's coming up pretty soon.
Right, yeah.
Okay.
Well, April.
We'll make sure we mention that in the next meeting then, and raise it, and put it out on the internet for our web service as well. Anything else? Okay, so it's on to our main presentation, and this is by Dr. Samantha Lawler. That doesn't look like a very small screen. At any rate, her presentation is on Planet 9, or Planet 9, a very good pun. Dr. Sam Lawler got her BSc from Caltech, and Caltech is also the home of Michael Brown. Michael Brown is a controversial character. He's the one who led the charge to demote Pluto from a planet status to a trans-Neptunian object. So I don't know if Sam made connections with him at that time, but she then went on to Wesleyan University and got a master's degree and got her PhD at University of British Columbia. And since 1915, she's been a Hertzberg Fellow at the...
I was good for my age.
You said 1950.
Thank you. You guys are sharp tonight. 2015, she's been at the Hertzberg Institute, and her main area of work is around debris disks around stars and planetary systems. So thank you so much for coming out on kind of dodgy weather conditions to make your presentation. Thanks. So
thanks. Okay, so I've been told to use the mic. This is good. Yes.
That's good.
Mm-hmm. Yeah. Okay. So I will continue from there. I can't look down, sorry. So while I was a student at Caltech, I did take a class from Mike Brown. I was actually taking a class from Professor Mike Brown. I was taking a class from him when he discovered Eris, or when he announced the discovery of Eris, which was, what demoted Pluto from planet status, right? And I had the amazing experience of going on, Caltech has a big tradition of geology field trips. So I got to go on a geology field trip that went to Lowell Observatory. And at that point, I got to listen to Mike Brown argue with the tour guide saying that Pluto is not a planet. Well, a few months later, after he announced the discovery of Eris, he said, well, Pluto should be a planet and Eris should be a planet too. So he really, really has wanted to discover a planet for a long time. So anyway, I'm going to talk about Planet 9 and the whole controversy surrounding that. So Pluto, the original trans-Neptunian object, I'm going to use TNO a lot in this talk. So Pluto was discovered at Lowell Observatory And it was discovered many decades before the second TNO was discovered, right? So that's part of the reason why Pluto was considered a planet, because it was the only known object out there for a very long time, even though there were many, many more theorized to be out there. It was decades before another was discovered. Over the years, we've gotten a better and better picture of what Pluto looks like until a few years ago when the New Horizons space probe flew past Pluto and took absolutely amazing pictures of it. I'll talk a little bit more about New Horizons again toward the end. But I mean, it's just incredible, right? I mean, every time I show you this, I have to point out, like, this is an actual picture. This is not an artist's rendition. This is an actual picture of the surface of Pluto with liquid nitrogen glaciers and water ice mountains floating on top of the glaciers. Like, it's just incredible. And atmosphere, you can see the layers of the atmosphere there. But it's not a planet. There's several reasons for this. Professor Mike Brown really owns that he is the one who got Pluto demoted, right? So he actually wrote a book on this. While I was working at Caltech after I graduated, we had a funeral for Pluto. So have you heard of the Rose Parade? In Pasadena, there's another parade called the Doodah Parade that makes fun of the Rose Parade, and basically anybody can be in it. So a group of us from Caltech got together and we had a funeral for Pluto, and Mike Brown was very happy to participate in that. So that was pretty fun. So that's why I'm in the index. So Pluto, in comparison with Eris, so Eris has now been shown to be slightly smaller than Pluto with the latest measurements, but it's actually a little bit more massive. So it is bigger in one sense. But there's a whole bunch of other Kuiper Belt objects, trans-Neptunian objects that have been discovered at this point that are almost as big as Pluto and on very similar orbits to Pluto. So it's not a planet if it hasn't cleared its orbit of similarly sized objects, is the definition that the International Astronomical Union settled on. So Pluto's not a planet. So at this point, we know about 3,000 or so TNOs. We think this is a model of what we think the Kuiper Belt looks like. We think there's about 400,000 TNOs out there larger than 100 kilometers in diameter, right? So there's a lot out there left to discover. So Reg introduced this very nicely. So I'm going to talk a lot about orbits. So just to define some terms that I'm going to use over and over. So the eccentricity of an orbit tells you how circular the orbit is. A circle has an eccentricity of 0, while a parabola has an eccentricity of 1, and unbound orbits have eccentricities larger than 1, so they come in for one pass and then never come back again. So this orbit up here has an eccentricity of maybe like 0.8, I would estimate. The closest point in the orbit to the sun is the pericenter, or perihelion, or periapse. The peri on the front is the important part. You can remember that by perilously close. Inclination is another useful parameter. Tells you about how tilted the orbit is relative to the plane of the solar system. Where all the planets in the solar system have a very are on almost the same orbital plane, within a degree or so of each other. And then another parameter I'll talk about a lot is the semi-major axis. So basically just how big is the orbit. So Earth's orbit is defined to have a semi-major axis of 1 astronomical unit, 1 AU. It's basically circular, very small eccentricity, almost 0. Neptune, for reference, is 30 AU. And the main Kuiper belt is between about 40 and 42 AU. So Sedna, for comparison, has its pericenter, so its closest approach to the sun, at about 76 AU, and has a semi-major axis of many hundreds of AU, right? It goes really, really far away from the sun. So just, for reference, for visualizing this, so Voyager 1 has been traveling away from Earth for 40 years, and it's at only 141 AU at this point, right? So hundreds of AU from the sun is really far away. So even further out is the Oort cloud, which we know about from occasional comets that come through on very large semi-major axis orbits. And this basically extends, we think, about halfway to the next star, so hundreds of thousands of AU. So that's pretty much our solar system. So bringing it back in, we're going to be talking about the Kuiper belt. So are there any questions up to this point? I'm very happy to answer questions as we go. Yeah.
One of your earlier diagrams seemed to show that the Kuiper belt had an inclination with respect to the ecliptic.
Oh,
is that the case, that on average TNOs are inclined?
Was that the let me, was that the oh dear, that's harder to see. Where's my mouse? Sorry, I'm lost in space. This one, yes.
Yes, that one.
Yeah.
Or is that just an illusion?
I think it's just an illusion. So kind of the average plane is basically the plane of the solar system. But there's quite a range of inclinations, right? So
oh, sure. But that's presumably an assumption of the model that generated the.
Yes, it is actually an assumption of this model, yeah. And there's actually been some work recently to try to measure the zero plane. And there were a couple of papers saying that it's tilted a little bit, and there's a couple of papers saying, nope, it's pretty much right where we expect it to be. So this is something that we're still trying to measure, but we think it's probably about the same. Yeah?
I think did I read something just lately that is it Voyager 1 that is just basically.
Yeah, I forget which one.
Itself out to outside of
the
solar system.
Yeah, well, so there's many.
Is that 141?
Yeah, well, so there's many different definitions of getting outside the solar system, right? There's, getting outside the solar wind and getting outside, there's into the interstellar medium and out, and this, so it's not like a neat boundary either. Like, I think one of the Voyagers, this is not my area of research, so I'm sorry if I say something wrong, but I know that it left and looked like it returned several times. Like it looked like it came back into the sun's magnetic field, and so the magnetic field is not like a neat boundary. There's some messiness to it, and it probably changes with solar weather. And but yes, there's it was in the news recently for having left one of these boundaries. Yeah, it's amazing because now we have like a really good map of what the solar system looks like in one line, right? So 2 lines maybe now, but yeah, that's all we've got. Yeah.
A couple of Oort cloud questions.
Sure.
What's it with the Oort cloud being more or less in the plane of the ecliptic?
So the Oort cloud's actually pretty circular. It's pretty spherical around the solar system. I'll talk about this a little bit more, but when you get really far out to really large semi-major axis orbits, tides from the galaxy are actually important. So, and what that does is it sort of circularizes the orbit. So if you made a map of just the average inclination, so imagine the plane of the solar system, as you go further and further away from the sun, it gets wider and wider. The inclinations get larger and larger as you go further out until they're at thousands of AU. They're pretty much circular around the solar system. Yeah, it's pretty crazy.
Well, the next question is kind of stupid.
How cloudy is the Oort cloud? What would be the average distance between?
Oh, it's probably very diffuse, right? Because there's I don't know, maybe a few planetary masses dispersed over many hundreds of thousands of AU, right? So in very small icy bodies, like kilometer size or 10-kilometer size, right? Like average comets. So it's very diffuse. But that's a good question. Yeah. Okay. I'll keep going here. So get out to. Okay. So we're back to the Kuiper Belt. So I study the orbital structure of the Kuiper Belt. So basically looking at where the orbits are, what the orbits are like in different places, and what this tells us about how the planets in our solar system moved around, which is pretty crazy. So there's kind of two main theories for how the planets in our solar system have moved around in billions of years ago. After the planets formed, after the gas, the original gas from the planetary nebula blew away, and we just had planets. We think that the planets moved. So there's two main theories for this. So these are both looking down on the solar system. You can see 4 giant planet orbits and a bunch of dots on the outside to represent the proto-Kuiper Belt, so the Kuiper Belt that originally formed. So there's smooth migration and the Nice model. So smooth migration is just like it sounds like. So the giant planets sort of scatter Kuiper Belt objects, and the combined effect of scattering lots and lots of little tiny bodies actually makes Neptune's orbit move outwards over time. And as it moves outwards, it sort of snowplows up Kuiper Belt objects. Yeah, like a snowplow, good Canadian analogy. The Nice model is much more chaotic. So the giant planets get scattered around a little bit, and then they actually gravitationally scatter each other, and boom, just destroy the Kuiper Belt in one time step in a computer simulation. And then Neptune circularizes, and that can trap Kuiper Belt objects into the orbits we see today.
What's going on with Uranus's orbit?
Oh yeah, so this in this particular Neptune, well in this scattering model, in this particular version, Uranus and Neptune actually flip places. Like Neptune started closer to the sun than Uranus, and they're not. So because it's chaotic, there's not really a right answer. It's just that they think something very violent happened and it could have been this. So these are kind of the two main ideas for how this could have proceeded. And by doing computer simulations and seeing what does the Kuiper Belt look like after this migration happens, and comparing that with what we see today, we can try to decide which of these better matches what actually happened in our solar system.
This is not a very long period of time. It's only 100 million years.
For the yeah.
It's very short.
Yeah, it is. Yeah. Relative to the age of the solar system. So we think this happened, 4 billion years ago or something. One idea with the chaotic scattering model in particular is that could have caused the late heavy bombardment on the moon, where 3.8 billion years ago, there's lots and lots of craters and flood basalts that happened because of lots of asteroids hitting the moon. And one possible way to explain this is if the giant planets went crazy, that would have destabilized a lot of asteroids also, right? So that's another line of reasoning for that particular model. In any case, we see that there are objects like Pluto that are in resonant orbit. So this is where so Neptune goes around the sun exactly 3 times in the same amount of time that Pluto goes around the sun exactly twice. And because of that, their orbits are more strongly coupled to each other. So if Neptune's orbit changes, Pluto's orbit can also change. Neptune is going to give gravitational kicks more efficiently to Pluto because it's in this resonance, and possibly captured Pluto in that resonance as it moved outwards. That was the original explanation for Pluto's orbit. So we can explain that kind of weird orbit that we see. Some other Kuiper Belt objects we see come pretty close to Neptune's orbit. So like Eris, for example, comes in pretty close to Neptune's orbit, so we think, oh, it could have had a kick from Neptune, a gravitational kick from Neptune that put it on the orbit that we see today. That makes sense. But then Sedna never gets closer to Neptune than like 50 AU away, right? So it couldn't have gotten a gravitational kick. It's not in a mean motion resonance with Neptune. So how did it get there? That's pretty weird. So this is showing a plot of, so on the x-axis is semi-major axis, so how big is the orbit, and paracentric distance, so how close is the orbit to the sun at its closest point, right? So there's a bunch of, can you see my mouse? No. Okay, so there's a bunch of Kuiper Belt objects that have really large paracentric distances. So Neptune is way down at the bottom of the plot at 30 AU, right? So if it has a paracentric distance of 30 AU, it crosses Neptune's orbit. So a whole bunch of these have really large paracentric distances. They never get very close to Neptune. So those are the ones that are hard to explain how they got there. And this is where the Planet 9 theory comes in. So, so the first 6 of these Kuiper Belt objects that were discovered that are on these high paracentric orbits that never come close to Neptune, they were all sort of pointed in the same direction. All of the orbits are pointed in one direction relative to the solar system, right? So the theory that was proposed by 2 professors at Caltech, including Professor Mike Brown, was that there's this giant planet. It's a 10 Earth mass planet on a 500 AU orbit that could be dynamically constraining all of these weird TNOs to have this kind of clustering. It was really presented in the news as a discovery that this planet had been discovered. It has not been discovered. This is a proposal for how to explain these weird orbits. And it's very interesting. But there's some serious observation biases that go into finding Kuiper Belt objects. So let's talk about that real quick. So Kuiper Belt objects, they don't make their own light, right? They're not like stars. We see them in reflected light. So light from the sun has to go all the way out to the Kuiper Belt object and then come all the way back to us. So if you move a Kuiper Belt object 10 times farther away, it's going to be 10,000 times fainter, right? So it's very sensitive to how far away it is. And then just because of Kepler's laws, the way orbits work, the TNOs will spend more time, if they're on eccentric orbits, they will spend more time farther away on the more distant parts of their orbit than in the closer parts of their orbit. So not only are they harder to see when they're farther away, but they spend most of their time there. So this is another bias against detecting particular orbits. So it's kind of like in the last few days, if you go out and look at a parking lot, all the cars that you see are trucks, right? The only cars that you can see are big giant trucks because we have the observation bias of a crazy snowstorm, right? We know that there is a distribution of cars that must exist, but the only ones that we can see are the biggest ones. So it's a similar thing with the Kuiper Belt. The only ones that we can see are the biggest ones and the ones that have a particular feature, like they in a particular direction or a particular type of orbit or four-wheel drive, same kind of thing. So the really terrible flaw in this line of reasoning is that these 6 Kuiper Belt objects were discovered in 6 different surveys, and we don't know the observing biases. So we don't know if the reason that they're all clustered like this is because they're actually clustered, or if because nobody looked in the other direction to see if there was something there, right? So unknown observing biases, this is very dangerous. So the solution is to have a TNO survey where we know the observing biases, we publish them, and we share them with everybody. So that's what we've done with the Outer Solar System Origin Survey, which is an international collaboration of about 40 astronomers from 8 different countries, but with very strong Canadian involvement. Everybody in red is either currently or recently at a Canadian institution. So we use the Canada, France, Hawaii telescope with Megacam on the telescope, right? So it's a huge camera, right? You can see people's hands in comparison. So it's great for finding lots of TNOs in one pointing. Finding TNOs is one of the best, the most exciting kinds of observing because they actually move from minute to minute on the sky, right? So the general observing strategy is you take a picture of a field, you go look at something else for an hour, come back, take another picture of that field, come back again in another hour, and then look for what moves. And you can actually, you know, right at the telescope, you can flip between the frames and try to find things that are actually moving. Of course, to do this well, we do this with software, but it is, for the OSSA survey, it was all still checked by humans at the end. So we do this for a patch of sky. So this is showing one of the observing blocks. You can see the date up in the left-hand corner and the moon phase for reference. And so each of those squares is one Megacam field on the sky. So we try to fill in this whole block and cover every single block about once a month for 5 months. And you can see, so those are the discovered TNOs, and you can see that they're moving. So this is letting us get a really good measurement of the orbit and predict where they will be in a year when that patch of the sky is in the right place for us to observe it again, right? So, so now it's been about 5 months. So now we can use those 5-month arcs to predict ahead. You can see where the TNOs will be 7 months later. And you can see even like that, there was one that just totally sheared off the field, right? It was a totally different kind of orbit, and we got that one too. So, so by doing this very carefully, we don't lose any of the TNOs that we discovered, which is not the case for most surveys. So this is what we discovered after 5 years of very careful observing. So including previous surveys, we discovered about 1,200 TNOs. So for reference, there were about 2,000 known for survey, and about 1,000 of them have been lost because their orbits were not well known enough. So we basically doubled the known TNOs. So this is a map. So imagine you're looking down on the solar system. Earth is basically in the center, right? At this scale, and these little blue wedges are showing those blocks on the sky where we covered very carefully. And all of the blue dots are TNOs that we actually discovered. And there's the galactic plane avoidance zone. So this is where the Milky Way is up in the sky. It's hard to find little moving fuzzy dots when there's even more fuzzy dots in the way, right? So, you know, every field of astronomy has something that they consider noise that other astronomers are very interested in. We don't like stars, so we didn't even try to look in those particular fields. And then there's gaps where the weather on Mauna Kea is not so great. So those are our biases. We have directional biases, we have orbital biases, but we know them all. And we can actually take into account all of the biases in our survey and test models to see if they match what we detected. So how do we test whether or not Planet 9 exists using this information? So the way that I do it is to use lots and lots of computers. It's really fun. Basically doing lots of computer simulations of how does Planet 9 affect orbits over millions and billions of year timescales. So we did this with, so this is one paper that I led talking about this. So we took, there's basically 3 different models of what we think the very distant Kuiper belt should look like. We did one with just the 4 known giant planets, one with Planet 9 on a circular orbit, and one with Planet 9 on an eccentric orbit. And basically what we find is that without Planet 9, all of the orbits are low inclination and have basically the same paracenter. They don't, they're only affected by Neptune. There's nothing to pull them to larger paracenter distances. When you put Planet 9 in, you get higher inclinations and higher paracenter distances. Planet 9 does this very efficiently. So if we take basically these scatter plots and make them into cumulative distributions, this is just a way that we compare these different models. So basically the point is that when we look at the semi-major axis, the inclination, and the perihelion distances of these 3 models are very different. But then we take these models and we say, if we observe these models with OSIS, what would we have detected? And when we do that, they all look exactly the same. That's really frustrating. so basically, it's because the difference is in this high paracenter population, right? So these are the ones that are the hardest to detect. And we would detect so few of those with OSIS that we actually would not be able to tell if the Kuiper belt looked like any of these 3 models. It basically would look the same to OSIS. But one thing that was really interesting that came out of this was we did not find this nice orbital clustering. Our orbits are all over the place. They're not confined by Planet 9 as is predicted. So that was kind of interesting. Okay, so another way to test this with computer models. This was led by Corey Shankman, who was a grad student here. Planet 9's orbit, and then the 6 Kuiper belt objects that are supposed to be confined by Planet 9. So if they're confined by Planet 9, they should stay there for billions of years, right? So up in the top left, you can see the time, and you can see that very quickly, well, solar system quickly. So within a billion years, they get wiped out all over the place. So Planet 9 is not keeping them confined in one direction. They're still processing all over the place. So that's kind of weird, because that was the entire reason that it was proposed. So then the observational way that we tested this is that OSIS discovered an equivalent group of high paracenter, very distant Kuiper belt objects. If this theory is right, then they should all be confined in the same direction. So what do you think? Do you think they will be confined, the new objects? How many people think they will be confined? No, they're not. They're not confined at all. They're all over the place. And when we actually run the statistics on this, this is consistent with a uniform distribution of distant Kuiper belt objects. So a more worrying way to look at this is, so this side is what the 6 confined Kuiper belt objects look like. This over here is where I've just set up a random distribution and then put in a particular set of constraints. I think for this I said, what if we were observing in the fall from Chile only? Then what would we have detected? What would be most likely to detect? And then just randomly pulling detections from that constraint, we get something that looks very similar from a uniform distribution. So basically, you can get this clustering entirely. I'm not saying that this is exactly what happened, but you could get this clustering entirely from observing biases. So
OSIS,
yeah.
OSIS, and you in particular, are a brown dream destroyer.
Yeah. Well, yeah. I don't see. It's not that I can't prove that Planet 9 doesn't exist, but I see no evidence that it does exist. So yeah. So yeah. So Planet 9 doesn't seem to actually cause any confinement in simulated Kuiper Belt objects. It doesn't keep the known Kuiper Belt objects aligned in long simulations. And a separate set of high paracentric Kuiper Belt objects are also not aligned. So OSIS says there's no evidence in favor of Planet 9. But let's talk about this a little bit more. So here's this plot again. So the paracenter distance versus semi-major axis, right? So the closest point to the sun versus how big the orbit is. So we can actually explain a lot of this with dynamical effects that we know about today without invoking some extra plan. So I talked about this a little bit in response to someone's question earlier. So out beyond 1,000 AU semi-major axis, then galactic tides actually will circularize the orbits and will change the paracenter distance. So basically everything out there we can explain just using physics that we know about. In this part here, the lower part of the plot, we can actually explain that from very weak gravitational kicks from Neptune. On these really large orbits, even the very weak kicks from Neptune can actually cause these to move around pretty well. So basically the only ones that we can't explain are Sedna and this newly discovered one, BP-113, nicknamed Biden, because thank goodness he was the BP when that was discovered. So those ones are weird, right? They're way up there. They're huge paracenter distances. They never get closer to Neptune than like 50 AU. But the thing that puzzles me the most, if my slide will change, oh no, is why is there nothing there? Why is there nothing? Well, because we should be, if we can detect those ones at really large paracenter distances, those are really hard to detect. We should be able to detect ones at lower paracenter distances, but there's nothing in that box. Pretty weird. So here's that same plot, but now with some extra simulations on it. So now I've put in a Planet 9 simulation, the green dot. So if you put Planet 9 in, Planet 9 also populates that box really nicely. If you put in a rogue planet, that also populates the box really nicely. So basically anything, any mechanism that you can come up with to make these really high paracenter TNOs also makes lots of slightly lower paracenter TNOs that we don't see. So that's weird. So basically, we don't know. We have no idea. This is right at the edge of what we're trying to understand right now. So these really distant high paracenter Kuiper Belt objects are really hard to discover, and we don't understand how they got there. We have no idea how they got onto those orbits. So one thing that I've been involved with a few people here at the observatory, as well as colleagues in Japan and Taiwan, is trying to do a better version of OSIS. So OSIS used the Canada-France-Hawaii telescope with a 4-meter mirror. We're proposing to use the Subaru telescope right next door, which has an 8-meter mirror, which, a lot more surface area, a lot more photons. We can detect way fainter Kuiper Belt objects. So we're working on that proposal right now, and hopefully it goes through. So that kind of wraps up the Planet 9 part of my talk. So if there's any questions, I would be happy to take those now. I have a little bit more to talk about, but let's talk about Planet 9 first. Yeah.
Do you still have time on the Canadian-France-Hawaiian telescope?
No, it's all been used up now. Yeah, OSIS is done. It's a complete survey. So now it's there's been, I think we're up to like the last accepted paper I think was like OSIS 16. And I know of at least 4 or 5 more papers that are in the works. So now it's just turn out papers and try to get all the science that we can out of the survey. Yeah. Yeah.
Yes, now as far as probe counts go, with the future telescopes like the 30 meter and the 38 meter,
Oh, yeah.
really large, and the James Webb, are they able to find more stuff with these future telescopes?
So the problem is that so with these really large telescopes, you need tons of money to go into them to build them. So the share of time that goes to each astronomer is very, very small. So to try to do a survey of any size on any particular type of astronomy is going to be very difficult. And especially for something like the Kuiper Belt, which is not as exciting as, I don't know what tax are going for these days, but that's, yeah, so I don't anticipate actually being able to do any sort of survey. What will be more interesting with those is probably characterizing in great detail a few objects, but probably just finding lots of them. I don't think we're going to get time on any of those really big ones. Yeah.
Just to revisit the survey that is now.
Yeah.
Your observation strategy, what was the duration of your exposures to get all of these?
Oh, I think there were, I'm on the theory side of things, right? So I get the orbits out after the rest of the team does their hard work there. But I think they were 5-minute exposures, might be less actually. But yeah, not huge long exposures. And that's mostly limited by the motion of the Kuiper Belt objects on the sky, right? You don't want them to trail too much because then it's harder to find them. So yeah, so really long exposures, you'd have really trailed Kuiper Belt objects. Yeah. Yeah.
So what does Michael Brown think of his former student?
Honestly, I think he just ignores me. Yeah. So there was actually a big Kuiper Belt meeting, and international Kuiper Belt meeting in Portugal last year, and neither Mike Brown or Constantine Batigan, the other author of that paper, they didn't come. It was really disappointing. So yeah, so I don't know. They're not. They have a lot of public support, and I don't see them coming and talking to the other astronomers very much. So that's my experience. So yeah.
Okay, all right.
Yeah.
That's very interesting. Thank you.
Yeah. Okay. So I will apologize in advance because so this next section, I had no idea that JJ Cavallars is going to be your next speaker. So I'm probably think of this as a preview for his talk because he's actually on the New Horizons team, so he will have a lot more insider information for you. But I've been so excited following what has been discovered about the tiny Kuiper Belt object MU69. So I just had to share that. So the MU69. Also, it's really fun because I've given this talk talking about what will we see, what will MU69 look like so many times, and now I get to talk about what it actually looks like. It's really cool. So, so this happened on January 1st, right? So this is just showing a map of the solar system, and that line shooting out from Earth is the New Horizons probe, flew past Pluto, and then it had the rest of the Kuiper Belt to fly through. So why waste a good space probe? We've got to find something for it to fly past. This, just for context, this is so Alex Parker, who was also a graduate student here at UVic several years ago, and now an astronomer in Colorado at Sperry. So he put together this movie. Oh, I guess there's sound too. Sorry. I hope it's not too loud. Oh well. Okay. He put together this movie of every single image taken as the New Horizons space probe flew past Pluto. Right. So it's getting closer and closer and closer, and taking pictures of Pluto and taking pictures of Charon and getting all sorts, and now getting the little moons. And getting close flybys of what does this surface look like? Oh my gosh, it's amazing! Glaciers everywhere. And so this is during the flyby, trying to get as much data as possible. And then it keeps going past Pluto. It turns around to look back. And these are actually my favorite images. Pluto itself is amazing, but looking back at the atmosphere of Pluto, backlit by the sun as it's flying away, it's just amazing. And watching Pluto get smaller and smaller and shrink off into the distance as the New Horizons probe just flew off into space, it really gives you a sense of just how empty it is out there. I mean, we know about thousands of Kuiper Belt objects, and we think there's hundreds of thousands out there, but there's not. It's crazy. So I thought that was an amazing movie that Alex Parker put together. So when the New Horizons probe was launched, the main target being Pluto, of course, and this was all of the Kuiper Belt objects that were known at that point in time, right? You'll notice, like I showed the map of Ossus, you'll notice that there's not very many Kuiper Belt objects near Pluto or in the other direction. So the reason for this is the same reason that Ossus had these gaps, right? That's where the plane of the galaxy is. So this is where there are not very many Kuiper Belt objects discovered because it's really hard to find anything there. So this is what we think the Kuiper Belt should look like, right? This is a model. So after the New Horizons probe flies past Pluto, which is on that white orbit, it should go through this really dense part of the Kuiper Belt, but there should be thousands and thousands of Kuiper Belt objects. But the problem is, this is what the search field looked like, right? So this is where they had to try to find Kuiper Belt objects in the Milky Way. This is hard. So Alex shared this image of where they're trying to find Kuiper Belt objects. You can't even see what a Kuiper Belt object would look like, right? There's actually a pixel underneath that arrow for reference, right? So you're supposed to find that moving around in all of those stars, right? So this is really hard, and they have to find something, right? The New Horizons probe is going. It's already on its way out. They have to find something else for the probe to fly past. So using Magellan and Subaru, they found a few things, right? So, and what's really interesting, so you'll notice there's the flight path of New Horizons, and the discovered Kuiper Belt objects are not right in line with that because they're moving, right? So not only do they have to find Kuiper Belt objects in the right place, they have to find them in the right place. So they'll be in the right place when the probe gets there, right? Because they're moving and the probe's moving. Like there's some crazy math that goes into this, just even to know where to look, right? So the New Horizons team got emergency time on the Hubble Space Telescope, which was much better. Still hard, but you can see that there's actually gaps between the stars because it's in space. There's no atmospheric blurring. Even looking at the galaxy, it's much easier. So I'm sure, yeah, you can ask. So JJ Cavallars was directly involved in this part, so be sure to ask him about this when he gives us a talk about the New Horizons stuff next month. So they were actually able to find several targets that were possible for the probe to get to with the fuel that it had left after the flyby. And one of them was so close that they barely had to burn any fuel to get there. So it's amazing that they were able to do this. I am super impressed. So they have this little dot that they can, after Pluto, they can use some fuel and get to that next little dot. So the next step is to try to learn as much as possible about that dot before they get there. The way they did this is amazing. So you can predict when occultations will happen. So once the orbit is really precisely measured, you can predict when that little tiny dot will go in front of a star, right, from a particular place on the Earth. So this is on the coast of Argentina, I believe. Is that right? Yeah. So they set up several, well, looks like a couple of dozen. They involved a lot of amateur astronomers, a few professional astronomers, and they set up along basically where this shadow was predicted to occur, right? And everybody set up their cameras with very high cadence, so many images per second of this one star, and watched for it to blink or not. And they had to synchronize their clocks very carefully. Like, it was a major undertaking, right? And they also needed people to just stare at the star and not see it blink, right? Because where it doesn't blink, they know that tells them how big the object is, right? So this was actually successful, which is amazing. Yeah, it was amazing. And from that, so these are basically where the shadow happened, and it was very strange looking, right? So not only did it wasn't just a sphere, and checked and rechecked, because this is a lot of people trying to work together with a bunch of telescopes that were shipped there and set up on random back roads, and lots of crazy conditions. So maybe that one is just shifted a little bit, but they checked and rechecked, and it looked like it was real. So what shape matches that? That's crazy, right? So it could be that it's a binary, and we just happened to catch it when the two pieces were right behind each other, or it could be some weird elongated shape, or it could be a contact binary, or someone on Twitter proposed maybe some other crazy shape. And then the flyby has happened now. It was so exciting. So I have a love-hate relationship with Twitter, but for watching this unfold, it was amazing. It was amazing. So December 30th, right? So the flyby actually happens on January 1st. There's also a huge, it's really far away, and the amount of data that it can send back over time is very, very slow, right? So there's a lot of delay here, and they can only send back some images. But so December 30th, the first images that are not just a pixel, right? So it's a few pixels, and it's long and skinny, so still don't know, is it long and skinny, or is it a contact binary, or what is it? And then they're actually able to measure the rotation, sort of, but they only have a few images to work with. So this is on December 31st. So December 1st, or January 1st, the flyby happened, and then they had to try to figure out where on the disk is the data that we actually want to get an image back, and prioritize that particular bit of data to get sent back. And so by January 2nd, they had this, and it was amazing. It's totally not what anybody was expecting, right? So it's a contact binary, which is crazy, right? So there's a whole bunch of planet formation models, and some of them predict that binary should be plentiful. So all of those theorists were very, very happy. So for comparison, this is pretty much exactly the same size as the Sandwich Peninsula, right? So it's like 30 kilometers in the long axis. And what's the most amazing part to me is how it perfectly matches that crazy occultation data, right? Perfectly. It was totally right. But so there are still a lot of surprises that'll come down, right? It's going to take about a year and a half for all the data to come down. So for example, last Friday on Twitter, I saw this, and it was crazy. So yeah, so that was images as, right, so they sent that image, basically seeing it face on as the spacecraft approached it. This was as it flew past. So that's weird. So the shape model that matches that is totally not a contact binary. It's flat. What? I had just convinced myself that a contact binary was reasonable. I have no idea. I have
But
no
now that you
idea.
see that, if you look at that high resolution image, you can see it's flat. It looks kind of like a dam.
But nobody would have guessed that. Nobody that I know of ever guessed that not only would it be a contact binary, but it'll be flat. There's no theorists who ordered this. So So the New Horizons probe is out there. It's got data sitting on its hard drive. It's slowly trickling data back to us. By the time JJ Cavallars comes and gives his talk next month, there will be more crazy things, I'm sure, coming out of this object. So yeah, so I just wanted to highlight that real quick. So yeah, I guess I will just sort of throw out my conclusions there. Right, so we know a lot about the orbital structure of the Kuiper Belt, but there's still a lot that we don't understand, and there will be a lot more discovered in the next few years. Right, we don't understand how to produce these high paracentric Kuiper Belt objects. Basically, every possible theory doesn't match what we see, so that's weird. We need to find more of these. These are the hardest ones to find. We need to find more in order to even make theories for how to produce these. Yeah, keep watching the news for more crazy images of MU69 that will break all of the theories that anyone's ever come up with. And there's a couple of websites up there if you're interested. So yeah, so thanks for listening, and please ask me questions.
Well, first of all, thanks for sharing your knowledge, but more importantly, thanks for sharing your enthusiasm. Yeah. It's such a fascinating topic, and have we got any questions for Matt here? Wow.
Yeah, yeah, that's what I said. What? Wow. Yeah.
So are you saying that there probably are hundreds of thousands of Kuiper Belt objects? Is that where people are at this point?
Yeah. So there's a size distribution of Kuiper Belt objects where there's a few big ones and you know, maybe 10 times more slightly smaller ones and 10 times more slightly smaller ones, right? So there's way more smaller ones than bigger ones, and the bigger ones are easier to see. So basically, as you go to fainter and fainter limiting magnitudes, you can find more and more of them, right? So, but yeah, so I think the estimate that I made was, yeah, 400,000 bigger than 100 kilometers. Yeah.
And are they named and are numbered? Are they given some?
The ones that are discovered, yeah, they're given numbers. So they first get something like 2014 MU69, and then as the orbit is more refined, I think it's 3 oppositions. I'm not sure what the definition is. Then if the orbit is well measured enough, then they get a number, a minor planet number, which is, I think they're up to 6 digits right now. And then, and at that point, the discoverer can propose a name to the IAU. And they take a very long time to decide if your name's official or not. So a lot of astronomers come out with silly names that get thrown all over the news, like Biden or whatever, because it's hard to remember 2012 VP113 or whatever. So, but yeah, so that's how that process works.
But there's about.
So there's about 3,000.
6 that are like about the same as Pluto that we know, or more?
Oh, well, I mean, depends on what you say by same size, right? Like over a few hundred kilometers, there's, I don't know, a dozen or so. Yeah, and there's probably not going to be too many more of those discovered. The ones that are big enough to pull themselves around, right? So to be dwarf planets by the IAU's definition, we've probably discovered most of those because those are the easiest ones to find. Those are the 4x4 trucks, right? So, yeah.
Because I do the programs in the schools.
Right.
So I'm always not quite sure exactly what to say. So I thank you, because that really makes a big difference. I like that, like, kind of know that I can say about a dozen are about there, but lots of little ones.
Yeah.
Thank you. That's good.
Yeah.
Is there any interest in tracking down more of the Kuiper Belt objects with the occultation time?
Oh yeah, so there's a whole team of researchers who do this, who calculate when occultations will happen, and that's a way to measure if there's an atmosphere, and it's a way to measure the exact shape. But it's a really tricky thing to coordinate, right? Because you have to get lots of astronomers lined up in some random part of the world at the right moment, right? So, so there are people who do this. I'm not personally involved with that kind of observation, but there's a whole team that does occultation and predictions. So yeah, and it's amazing. It's amazing the amount of information you can get out of it. Yeah.
It's a frugal way to conduct these long missions, isn't it? So,
yeah.
And yeah, we get a pathway was a really nice place.
Yeah.
Any other questions? Well, I remember about 4 years ago, it was Chris Gaynor who organized a party at Pluto's restaurant, and many of you were there to watch the flyby of New Horizons and celebrate that event. And I felt kind of depressed after that because I figured we'd gone by the end of the line. There's not much else out there, and you've shown us there's a ton of stuff out there.
And this is a tiny one, right?
Yeah. So I think that it's not a career-ending opportunity. It's a career. There's a whole new world out there to explore. So that was just wonderful. So thank you so much again, Sam, for braving the harsh weather to come out here and sharing your research, and we wish you well. As a token of appreciation, we have this is a water bottle that celebrated our 100th anniversary of the RAS Center, and it's also suitable for white wine. So thank you so much. So we traditionally go up to the 4th floor astronomy lounge of the Elliott building for coffee, tea, and cookies. And you're most welcome to join us up there. The other thing is that I heard reports that it's getting slippery out in the parking lots there. So when you're heading out to your car and getting in your car and maneuvering your car on the way home, do take care. And thank everyone for